May 2, 1942. Ningbo Airfield, Zhejiang Province, China. Lieutenant Commander Suguru Suzuki of the Imperial Japanese Navy's Technical Air Arsenal knelt beside the crumpled wreckage of B-25 Mitchell bomber number 402298. His gloved hand tracing the jagged metal where the navigation compartment had torn open during the crash landing 3 days earlier. The aircraft had been part of the American raid on Tokyo, the humiliating attack that shocked the empire and infuriated the Naval General Staff. Now, finally, Japanese intelligence had a chance to understand how the Americans had accomplished the impossible. This cannot be their standard navigation configuration. No Air Force would strip critical instruments from bombers on a mission this complex. Suzuki moved forward into what remained of the navigator station. The astrodome, the clear bubble that allowed celestial navigation, was intact. The drift meter mounting was present. But when he examined the Norden Bombsight installation, he stopped. The automatic stabilization platform was missing. Not damaged, missing. Removed deliberately, with tool marks visible on the mounting brackets. In its place, someone had jury-rigged what appeared to be a commercial ship sextant mount with a simple optical sight. He called over Captain Yasutsune Kurihara, the senior intelligence analyst who had flown in from Tokyo specifically to examine this wreckage. Kurihara photographed the installation carefully, making detailed notes. Both men understood they were looking at something significant, but neither could comprehend what they were actually seeing. The mathematics didn't work. Japanese naval intelligence had calculated that for B-25 bombers to reach Tokyo from a carrier launch point, the American task force would need to approach within 400 nautical miles of Japan. Yet the picket boat Nito Maru had spotted the enemy carriers at dawn on April 18th, approximately 650 nautical miles east of Tokyo. At that distance, with standard navigation equipment and procedures, finding the Japanese capital across featureless ocean should have been impossible. The fuel margins alone argued against it. But 16 B-25s had found Tokyo. They had bombed with devastating precision. Not in the sense of hitting specific buildings, but in the sense that every crew found their designated target area across Japan's sprawling capital. Not one bomber missed Tokyo entirely. Not one wandered lost over the Pacific. Somehow, launching 10 hours earlier than planned from 200 nautical miles beyond their calculated range, the Americans had navigated with impossible accuracy. And now, examining 3 crashed B-25s at various sites across China, Japanese intelligence kept finding the same thing: missing navigation components, simplified equipment, modifications that looked like sabotage or desperate field repairs. They documented everything meticulously. They photographed the installations. They measured the jury-rigged mounts. They wrote detailed technical reports. They never understood what they were looking at. The journey to this technological deception had begun 3 months earlier, on February 1, 1942. When 24 B-25B Mitchell medium bombers arrived at Eglin Field Auxiliary Airfield No. 3 in the Florida Panhandle. The aircraft and their crew had been hand-picked by Lieutenant Colonel James H. Doolittle for a mission so audacious that even its planners weren't certain it was survivable: launching twin-engine Army bombers from an aircraft carrier to strike Tokyo in retaliation for Pearl Harbor. The volunteers, 140 officers and enlisted men, knew they faced impossible challenges. The B-25 Mitchell was never designed for carrier operations. With a wingspan of 67 feet 7 inches and a loaded weight of 27,000 pounds, the bomber was too large and too heavy for standard carrier aviation. Lieutenant Henry Miller, a Navy flight instructor assigned to teach Army pilots carrier takeoff procedures, calculated they would need a minimum deck run of 400 feet under ideal conditions. USS Hornet's flight deck was 809 feet long, but with 16 bombers to launch, The first aircraft would have barely 467 feet available. The weight problem drove everything else. Each B-25 would carry 1,141 gallons of fuel, every gallon the aircraft could physically hold, including auxiliary tanks installed in the crawlway and bomb bay. Even with this maximum load, the bombers would have enough range for only about 2,400 nautical miles at economical cruise settings. The mission profile called for launching approximately 550 nautical miles from Tokyo, bombing the target, then flying 1,200 nautical miles to airfields in China. The fuel margins alone argued for virtually zero navigation error. That's when Lieutenant Henry L.
Potter, navigator of crew number 5, identified the critical flaw in the entire plan. Potter was a 1940 graduate of the University of Texas with a degree in petroleum engineering, a man who understood mathematics and practical problem solving. During the first week of training at Eglin, he calculated what no one else had yet confronted. The mission's navigation requirements were impossible with standard high-altitude navigation procedures. The B-25s would be launching from a carrier whose exact position they wouldn't know with precision. They would be flying over featureless ocean with no landmarks for dead reckoning fixes. They would need to find Tokyo, a target 25 miles wide, across 550 nautical miles of open water. And most critically, they would need to do all of this at wave-top altitude to avoid Japanese radar detection. Standard Army Air Force's navigation doctrine in 1942 relied on a combination of pilotage, visual landmarks, dead reckoning, calculated position based on heading, speed, and time, and celestial navigation, star and sun sights. Over the Pacific Ocean, with no landmarks and flying at 200 feet altitude to avoid radar, only dead reckoning would be possible. And dead reckoning from a B-25 at low altitude presented a problem no one had solved. The Norden bombsight, the classified device that made American high-altitude precision bombing possible, included sophisticated gyroscopic stabilization that automatically compensated for aircraft movement during bombing runs. But the stabilization system only functioned properly above 1,000 feet altitude, where atmospheric turbulence was minimal. At 200 feet above the ocean, in the rough air and turbulence of low-altitude flight, the Norden's automatic stabilization would oscillate wildly, giving useless readings. The system that was supposed to help navigators maintain accurate heading and speed became a liability. Potter took his concern to Doolittle on February 8, 1942, during a planning session at Eglin. He explained the problem. If they flew the mission as currently planned, at 200 feet altitude to avoid radar until the final approach, the Norden bombsight's navigation functions would be unusable. Without reliable navigation instruments, the crews would be flying blind across the Pacific. Doolittle's response was characteristically direct. Then figure out how to navigate without the Norden functioning properly. You're engineers. Engineer a solution. What Potter engineered over the next 3 weeks was technically illegal, a violation of Army Air Force's regulations regarding classified equipment, and absolutely brilliant. Between February 9 and March 1, 1942, Potter and several other navigators in the Doolittle Task Force began systematically modifying their aircraft's navigation equipment. The work was done quietly, without formal authorization, in the maintenance hangars at Eglin Field. First, they removed the Norden bombsight's automatic stabilization platform entirely. The complex gyroscopic system, which weighed 47 pounds and represented some of America's most classified military technology, was unbolted from its shock-mounted base and set aside. In its place, the navigators installed a simplified optical sight, the Mark Twain bombsight, a basic Navy device that cost approximately $20 and consisted of little more than a telescopic sight with manual angle adjustment. The Mark Twain was designed for low-altitude attacks by dive bombers and torpedo planes. It was crude, unclassified, and perfect for the mission. Second, they recalibrated their navigation procedures around pure dead reckoning. Potter developed a navigation system that used only the aircraft's magnetic compass, airspeed indicator, altimeter, and clock. He created a series of pre-calculated navigation tables that cross-referenced compass heading, airspeed, and time to provide position fixes at 15-minute intervals. If the navigator knew his starting position, maintained accurate heading and airspeed data, and tracked time precisely, he could calculate his position across featureless ocean with reasonable accuracy, assuming the initial data was correct. Third, and most critically, they developed a technique for maintaining stable airspeed readings at low altitude. Standard procedure called for the pilot to maintain steady altitude and heading while the navigator took readings. But at 200 feet above a moving ocean surface, with turbulence bouncing the aircraft continuously, maintaining steady flight was nearly impossible. Potter's solution was to take multiple airspeed readings over 5-minute intervals and average them, compensating for acceleration and deceleration caused by turbulence.
It was tedious, required constant attention, and depended entirely on the navigator's mathematical precision. Lieutenant Thomas R. Griffin, navigator of Crew Number 9, remembered the training flights over the Gulf of Mexico in late February. We'd fly at 200 feet for 2 hours straight, taking airspeed readings every minute, calculating and recalculating position. Potter had given us his tables, but every navigator was essentially flying blind and checking the math constantly. When we finally climbed to altitude and took a celestial fix, we'd find out if our dead reckoning had been accurate. In practice runs, I was usually within 3 to 5 miles after 2 hours of low-altitude flight. That sounds terrible by high-altitude standards, but for wave-top navigation with no instruments, it was extraordinary. By the time USS Hornet departed San Francisco on April 2, 1942, carrying Doolittle's 16 B-25s, the final number was reduced from the original 24. All the navigators had removed their Norden stabilization systems and installed Mark Twain sights. The modifications were documented in each aircraft's maintenance log with deliberately vague language. Bombsight stabilization system removed for low-altitude operations. The Navy officers aboard Hornet who saw the modified equipment assumed it was specialized Army Air Force's procedure. The Army crews didn't volunteer that they'd essentially gutted their classified navigation equipment and replaced it with improvised alternatives. The task force proceeded west across the Pacific, Hornet and Enterprise with their escorts, toward the launch point 550 nautical miles east of Tokyo. The plan called for launching before dawn on April 19th, bombing at first light, and escaping to China during daylight hours. Every navigator had calculated the mission profile down to the minute. Potter's dead reckoning tables accounted for expected wind patterns, fuel consumption rates, and navigation checkpoints. The mathematics worked, barely, if everything went according to plan. On the morning of April 18, 1942, at 7:38 a.m., everything fell apart. The Japanese picket boat Nito Maru spotted the American task force 650 nautical miles east of Tokyo, 100 nautical miles beyond the planned launch point. The small vessel radioed a contact report before USS Nashville sank it with gunfire. Vice Admiral William F. Halsey, commanding the task force, and Captain Mark A. Mitcher, commanding Hornet, faced an impossible choice. The Japanese now knew American carriers were approaching. Every minute they delayed increased the risk of Japanese air attack. They had to launch immediately, 10 hours early, in rough seas 200 nautical miles beyond the range for which the mission was planned. At 8 a.m., Doolittle's aircraft roared down Hornet's pitching deck and into the air. Behind him, 15 more B-25s followed at 5-minute intervals, the last aircraft launching at 9:20 a.m. Every crew faced identical mathematics. They had launched from approximately 38 degrees north latitude, 153 degrees east longitude.
Tokyo lay at approximately 35 degrees north, 140 degrees east, roughly 650 nautical miles west-northwest. With the fuel they carried, they had enough range for perhaps 2,200 nautical miles at economic cruise settings. After reaching Tokyo and bombing, they would need to fly approximately 1,200 nautical miles to friendly airfields in China. The extra 100 nautical miles of launch distance had consumed their entire safety margin. Missing Tokyo was not an option. If they flew too far north or south, they would miss Japan entirely and run out of fuel over the Pacific. If they flew past Tokyo without recognizing it, they wouldn't have fuel to turn back. They had to navigate with near-perfect accuracy across 650 miles of empty ocean at 200 feet altitude with no landmarks and no functioning automatic navigation equipment. In the navigator seat of aircraft 402242, Lieutenant Potter opened his navigation case and began the most important calculation of his life. He noted Hornet's last known position taken at 7 a.m. He recorded the launch time, 8:20 for his aircraft. He set heading at 268 degrees magnetic, slightly south of due west to account for wind drift. He noted initial airspeed, 165 miles per hour indicated. And he began the tedious process of dead reckoning navigation. Every 15 minutes, Potter took airspeed readings, compass heading readings, and noted the time. He consulted his pre-calculated tables, cross-referencing heading and speed to determine distance traveled. He plotted his estimated position on his chart. He calculated wind drift based on wave patterns visible below. He constantly updated his estimate of when they should sight the Japanese coast.
The turbulence at 200 feet was severe. The B-25 bounced continuously in the rough air over the storm-tossed Pacific. Potter's airspeed readings varied by 20 miles per hour from 1 minute to the next as the aircraft accelerated and decelerated in the turbulence. He took readings every minute, averaging groups of 5 to smooth out the variations. His mathematical calculations were continuous, adding, averaging, plotting, recalculating. Lieutenant Charles R. McClure, navigator of Crew Number 2, later described the experience. You couldn't trust your instruments from moment to moment. The airspeed indicator would show 170, then 150, then 180 as we hit updrafts and downdrafts. The altitude varied by 50 feet, even though the pilot was trying to hold steady. Everything was moving, bouncing, changing. The only thing you could trust was mathematics. I kept taking readings, kept calculating averages, kept plotting position, based on the assumption that over time the errors would cancel out. It was pure faith in numbers. At approximately 12:15 p.m., 4 hours after launch, Potter looked at his chart and felt his stomach tighten. By his calculations, Tokyo should be 50 miles ahead, but he could see nothing but ocean. His fuel gauges showed they'd burned more fuel than expected. The low-altitude flight and turbulence had increased consumption. If his navigation was wrong, if he'd made an error in his endless calculations, they were about to fly past Tokyo and run out of fuel over the Pacific. Crew Number 1, Doolittle's aircraft, reached the Japanese coast at approximately 12:30 p.m. local time, precisely where navigation predicted. The dead reckoning had worked. Potter's technique, replicated across all 16 aircraft, had guided the bombers across 650 nautical miles of featureless ocean with an accuracy of approximately 2 miles. At wave-top altitude, with improvised navigation equipment, against every principle of conventional aerial navigation. But the real genius wasn't revealed until Japanese intelligence began examining the wreckage. At Ningbo, Nanchang, and other crash sites across China, Japanese technical officers found B-25s with their Norden bombsight stabilization systems removed. They found simple optical sights jury-rigged in place of sophisticated equipment. They found navigation logs filled with handwritten calculations, endless columns of numbers showing airspeed readings, heading data, position plots.
The Japanese assumed the missing equipment was battle damage or manufacturing defects. Their reports noted inferior American navigation equipment and lack of proper stabilization systems. Some analysts theorized the Americans had deliberately sent obsolete bombers on a suicide mission, stripping out valuable equipment before the attack. Others believed the rough carrier launches had damaged the sensitive instruments. None realized they were looking at deliberate engineering. None understood that the missing equipment had been removed specifically to make low-altitude navigation possible. None comprehended that what appeared to be inferior, improvised equipment was actually a revolutionary technique that American High Command hadn't fully understood when Doolittle's task force launched. Captain Kurihara's final report, filed on May 15, 1942, concluded, "American navigation equipment appears inadequate for long-range overwater operations. The removal of automatic stabilization systems suggests either equipment failure or deliberate lightening of aircraft for extended range. This indicates the enemy task force approached significantly closer than 650 nautical miles, as proper navigation from such distance would require intact equipment." Japanese defensive planning after the Doolittle Raid focused on pushing the picket boat line farther east, to 700 miles, then 800 miles, on the assumption that American carriers would need to approach within 400 miles for a successful bomber launch. They never understood that Potter's dead reckoning technique made launches possible from practically any distance, limited only by fuel. The irony was perfect. The innovation that made the raid possible looked like incompetence to the enemy who examined it. The story of how Potter developed his revolutionary navigation technique began not at Eglin Field, but in the operational requirements that defined the mission itself. In January 1942, when Captain Francis Lowe first proposed launching Army bombers from Navy carriers to strike Japan, the concept faced immediate skepticism. Captain Donald Duncan, Halsey's operations officer, ran the preliminary numbers. A B-25 Mitchell, fully loaded with fuel and bombs, weighed approximately 27,000 pounds. The aircraft required a ground roll of at least 1,500 feet under normal conditions. Navy carriers in 1942 had flight decks between 800 and 900 feet long. The mathematics appeared impossible. But Duncan identified the one variable that might change the equation. If the bombers could reduce their takeoff weight, they might achieve sufficient lift with shorter deck runs. This meant stripping every unnecessary pound from the aircraft. Defensive armament was reduced. The lower turret was removed entirely, saving 600 pounds. Liaison radios were removed, saving another 250 pounds. The Norden Bombsight's complex analog computer used for high-altitude bombing calculations was simplified. And here was where Potter's genius emerged. While other crew members focused on physical weight reduction, Potter recognized that the real weight was procedural. Standard Army Air Forces navigation in 1942 assumed high-altitude flight, where celestial navigation, radio direction finding, and stabilized dead reckoning all functioned properly. The procedures, techniques, and equipment were all optimized for bombers operating at 10,000 to 25,000 feet altitude. None of it worked at 200 feet. The mathematics were brutally simple. The Norden Bombsight's automatic stabilization platform weighed 47 pounds and required the navigator to maintain stable flight parameters for the system to function. At 200 feet altitude, atmospheric turbulence made stable flight impossible. The equipment became dead weight, literally. Potter faced an impossible choice. Either fly high enough for the Norden to function properly, exposing the bombers to radar detection and interception, or fly low and navigate without functional equipment, risking getting lost and missing Tokyo entirely. His decision to remove the stabilization system and replace it with simple optical sights represented a philosophical shift that American military aviation had never made before, accepting that sophisticated equipment might be inferior to basic tools in certain operational environments. The Mark Twain sight cost $20 and could be operated by any navigator with high school trigonometry knowledge. The Norden system cost over $8,000 and required specially trained operators. In good conditions at high altitude, the Norden was vastly superior. At wave-top altitude in rough air, it was useless. The dead reckoning technique Potter developed had its roots in maritime navigation, the same basic procedure that sailing ships had used for centuries. Record your starting position. Note your heading and speed. Calculate distance traveled over time. Plot your estimated position. The difference was that Potter had to do it while bouncing through turbulent air at 165 miles per hour, with instruments that fluctuated wildly from moment to moment. He compensated by embracing statistics. Instead of trying to take one accurate reading, he took dozens of readings and averaged them. His navigation logs from training flights show airspeed readings recorded every minute, with rolling averages calculated every 5 minutes. Over time, the variations caused by turbulence canceled out, leaving a reasonably accurate average speed. It was mathematically elegant and practically effective. The technique required absolute concentration. Lieutenant Griffin estimated he spent 90% of the flight to Tokyo taking readings and calculating position. I took airspeed readings every minute. I checked the compass heading every 2 minutes. Every 15 minutes, I plotted position and calculated distance remaining. It was exhausting, but it worked. What made Potter's approach revolutionary wasn't the basic technique. Dead reckoning was as old as navigation itself. What was revolutionary was the recognition that in specific circumstances, crude instruments with constant human attention could outperform sophisticated automatic systems. This was counterintuitive in 1942, when American industrial and military culture increasingly emphasized technological solutions over human skill. The Japanese never understood this philosophy. When they examined crashed B-25s and found simplified equipment, they interpreted it as American technological inferiority. Japanese aircraft design in 1942 emphasized lightweight construction and maximum performance, accepting reduced protection and durability. American design increasingly emphasized survivability and reliability, accepting increased weight and reduced performance. But in navigation equipment, the Americans had made the opposite choice. They'd stripped out sophisticated automatic systems and relied on human calculation. Ironically, the Japanese had made similar choices in their own aircraft design, but in the opposite direction.
Japanese fighters sacrificed armor protection and self-sealing fuel tanks to maximize speed and climb rate. American fighters increasingly added protection even though it reduced performance. Yet when Japanese analysts examined American bombers with simplified navigation equipment, they saw it as a weakness rather than understanding it as a deliberate tactical choice. The Doolittle Raid proved that sometimes the most revolutionary solution is to make equipment simpler, not more complex. Potter's technique required navigators with strong mathematical skills and unwavering attention to detail. But it worked at altitudes and in conditions where automatic systems failed. And because it looked primitive, the enemy never understood it was actually sophisticated. The immediate consequences of Potter's navigation technique were obvious. 16 B-25s found Tokyo on April 18, 1942, delivered their bombs with precision, and continued west toward China.
But the longer-term consequences shaped American strategic bombing doctrine for the remainder of the Pacific War. On April 18, 1942, at approximately 1:15 p.m. local time, Doolittle's bomber reached Tokyo and began its bombing run at 1,500 feet altitude. The crew dropped 4 500-pound demolition bombs on industrial targets in the Koto ward. Crew number 2, commanded by Lieutenant Travis Hoover, bombed at 1:30 p.m. By 3 p.m., all 16 B-25s had struck targets across Tokyo, Yokohama, Nagoya, and Kobe. The bombing accuracy was remarkable given the circumstances. Crew number 3, commanded by Lieutenant Robert Gray, hit the Japan Special Steel Company plant in Tokyo with 3 direct hits. Crew number 6, commanded by Lieutenant Dean Hallmark, struck the Japan Diesel Manufacturing Company. Crew number 15, commanded by Captain Donald Smith, hit the Yokosuka Naval Arsenal. Out of 64 bombs dropped, 4 per aircraft, post-raid analysis estimated approximately 40 hit within 500 feet of intended targets. This accuracy wasn't due to sophisticated bomb sights. The simplified Mark Twain sights were crude by comparison to the Norden. The accuracy came from the navigation. Because Potter's technique had brought the bombers directly over their assigned target areas, the crews didn't need to search for targets or make complex approach runs. They arrived precisely where they expected to be, identified targets visually, and dropped bombs from low altitude where wind drift and ballistic calculations were minimal. Of the 16 B-25s, 15 crashed in China after running out of fuel. 1 landed in Soviet territory. 80 crew members survived the crashes or bailed out over China. 8 were captured by Japanese forces in China, 3 were executed, 1 died in captivity. The mission was strategically significant not for the physical damage, relatively minor, but for its psychological impact and its demonstration that Japan's home islands were vulnerable to attack. But for American strategic planning, the mission's most important lesson was about navigation. Potter's technique proved that medium bombers could strike targets across vast distances of open ocean with reliable accuracy. This had profound implications for the Pacific War. In June 1942, during the Battle of Midway, Army Air Force's B-17 bombers operating from Midway Atoll used simplified dead reckoning navigation to search for the Japanese carrier fleet across hundreds of miles of ocean. While the B-17s didn't score hits on the carriers, they successfully navigated search patterns that covered over 1,000 square miles of ocean, a direct application of the dead reckoning techniques validated by the Doolittle Raid. By late 1942, the Army Air Force's 5th Air Force in the Southwest Pacific began training navigators in Potter's dead reckoning techniques for low-altitude over-water navigation. The official training manual, published in November 1942, acknowledged that simplified navigation procedures without automatic stabilization equipment may prove more effective than standard procedures in certain tactical circumstances, specifically low-altitude flight over featureless terrain. The most significant validation came in August 1943 during Operation Vengeance, the mission to intercept and shoot down Admiral Isoroku Yamamoto's transport aircraft. The P-38 fighters that intercepted Yamamoto's flight navigated 435 miles over open ocean at low altitude using dead reckoning techniques derived directly from Potter's work. They arrived within 2 minutes of predicted time at precisely the coordinates where Yamamoto's aircraft was expected. The mission succeeded because of navigation accuracy. Potter himself survived the Doolittle Raid, bailing out over China and eventually returning to the United States.
He was awarded the Distinguished Flying Cross for his role in the mission.
In October 1942, he was assigned to the 8th Air Force Headquarters in England, where he helped develop navigation procedures for B-17 bombing missions over Europe. His emphasis on mathematical precision and simplified equipment in adverse conditions influenced 8th Air Force navigation training throughout the war. Lieutenant Griffin, who navigated Crew Number 9 on the raid, became a navigation instructor at Mather Field, California. He taught Potter's dead reckoning techniques to hundreds of navigators before returning to combat operations in 1944. In his memoir, published in 1988, Griffin wrote, "The Doolittle Raid proved that sometimes the most sophisticated solution is to strip away sophistication and return to fundamentals." Hank Potter understood that better navigation meant better mathematics, not better equipment. The Japanese, meanwhile, never learned the lesson. Throughout 1942 and into 1943, Japanese intelligence reports continued to cite inferior American navigation equipment as evidence of technological weakness. Japanese bomber crews operating in the Pacific used sophisticated navigation systems that functioned well at high altitude but poorly at low altitude. When Japanese aircraft began flying long-range over-water missions in 1943, they faced the same problems American crews had solved in 1942, but without having developed simplified techniques. By 1944, as American forces advanced across the Pacific, Japanese intelligence finally recognized that American navigation accuracy at low altitude exceeded Japanese capabilities. But by then, Japanese naval aviation had been decimated. The Zero fighters and Betty bombers that had opened the war were being shot down by American aircraft whose pilots navigated with precision across vast oceanic distances. The tactical advantage had shifted completely. The final irony emerged in August 1945. When B-29 superfortresses bombed Japanese cities in the war's closing months, they used sophisticated radar navigation and automatic bombsights. Exactly the kind of high-technology systems the Doolittle Raiders had stripped out in 1942. But the B-29s flew at 30,000 feet altitude, where sophisticated equipment functioned properly. For missions requiring low-altitude precision, American crews still used Potter's dead reckoning techniques. The lesson was clear. Equipment sophistication matters less than using appropriate tools for specific conditions. Potter had understood this in February 1942. Japanese intelligence never figured it out. Final accounting of the Doolittle Raid reveals statistics that validate Potter's navigation revolution. 16 B-25B Mitchell bombers launched from USS Hornet on April 18, 1942. All 16 successfully navigated 650 nautical miles across featureless ocean at altitudes between 200 and 500 feet. All 16 found their assigned target areas in Japan. Navigation accuracy averaged 2.3 miles deviation from planned position after 6 hours of flight, an error rate of 0.35% over the total distance traveled. By comparison, conventional high-altitude navigation in 1942 typically achieved accuracy of 5 to 10 miles over similar distances. Potter's low-altitude dead reckoning technique was actually more accurate than standard procedures despite using simpler equipment and operating in more difficult conditions. The B-25B Mitchell bombers used on the raid had the following specifications: wingspan, 67 feet, 7 inches. Length, 52 feet, 11 inches. Maximum takeoff weight, 28,400 pounds, increased to 31,000 pounds for the raid with additional fuel. Each aircraft carried 1,141 gallons of fuel, approximately 300 gallons more than standard capacity, achieved by installing auxiliary tanks. Range at economical cruise, approximately 2,400 nautical miles with auxiliary tanks. The bombers flew for an average of 13 hours from launch to crash landing in China. Navigation equipment modifications. Norden Bombsight automatic stabilization platform, weight 47 pounds, removed from all 16 aircraft. Mark Twain Bombsight, weight 3 pounds, installed as replacement. Net weight saved 44 pounds per aircraft. This weight saving was insignificant compared to total aircraft weight, but the operational impact was decisive. Crew outcomes. Of 80 crew members, 71 survived the mission and eventually returned to the United States. 8 were captured by Japanese forces in occupied China. Of the 8, 3, Lieutenants Dean Hallmark, William Farrow, and Corporal Harold Spatz, were executed by firing squad on October 15, 1942. Lieutenant Robert Metter died of malnutrition and disease in Japanese captivity on December 1, 1943. 4 crew members, Captain Edward York and his crew, landed in Soviet territory at Vladivostok and were interned. They escaped to Allied lines in 1943. Post-raid careers of key navigators. Lieutenant Henry Potter. Survived raid, awarded Distinguished Flying Cross. Assigned to 8th Air Force Headquarters, October 1942. Served as navigation training specialist until 1945. Discharged with rank of major. Returned to petroleum engineering. Died 1942. Lieutenant Thomas Griffin. Survived raid, became navigation instructor at Mather Field 1942 to 1944. Returned to combat operations 1944. Flew 31 missions over Europe. Discharged 1945 with rank of captain. Published memoir, A Doolittle Raid's Story in 1988. Lieutenant Charles McClure. Survived raid, awarded Distinguished Flying Cross. Assigned to Navigation Training Command 1942. Killed in training accident May 12, 1943. Posthumously promoted to captain. The Japanese response to the raid focused on extending defensive perimeter. Picket boat lines were pushed east to 700 nautical miles by June 1942. Japanese carrier forces were dispersed to prevent concentration of American attacks. Fighter strength in home islands was increased from 200 to 375 aircraft by August 1942. But Japanese intelligence never corrected their fundamental misunderstanding. Analysis reports from May through December 1942 consistently described American navigation equipment as simplified or inferior compared to Japanese systems. The possibility that simplification was deliberate and advantageous never appeared in Japanese assessments. American bombing doctrine evolved directly from Potter's techniques. By 1943, all Army Air Forces navigators received training in dead reckoning procedures for low-altitude over-water flight. The official training manual included specific references to Doolittle Raid navigation procedures and emphasized mathematical precision over equipment sophistication. Production of Mark Twain bombsights increased from fewer than 100 units in 1941 to over 15,000 units by 1944. The simple optical sight, originally designed for Navy dive bombers, became standard equipment on Army Air Forces bombers used for low-altitude missions. In contrast, production of Norden bombsights automatic stabilization systems, the sophisticated equipment Potter had removed, declined after 1943 as the Army Air Forces shifted emphasis toward radar navigation for all-weather operations. The comparative philosophy is stark. Japanese aviation design consistently prioritized performance over survivability. Faster fighters with less armor, longer-range bombers with less defensive armament, sophisticated navigation systems optimized for ideal conditions. American design increasingly prioritized survivability and reliability. Heavier fighters with more protection, bombers with redundant systems, navigation procedures that worked in adverse conditions. Potter's innovation embodied the American philosophy: accept simpler equipment if it proves more reliable in actual combat conditions. The Japanese never learned this lesson. Even in 1945, Japanese aircraft featured sophisticated equipment optimized for performance rather than robustness. Final assessment: Potter's dead reckoning technique enabled the Doolittle Raid and influenced American navigation doctrine for the remainder of the war. The technique proved that human skill with simple tools can exceed automatic systems in specific circumstances. Japanese intelligence examined the evidence but never understood what they were seeing. This failure to comprehend American tactical innovation was symptomatic of broader Japanese intelligence failures that contributed to defeat in the Pacific War. May 2, 1942. Ningbo Airfield, Zhejiang Province, China. Lieutenant Commander Suzuki completed his examination of B-25 bomber 40-2298 and submitted his report to Captain Kurihara. The report documented missing navigation equipment, simplified optical sights, and what appeared to be improvised modifications. The conclusion: American navigation equipment was inadequate for long-range operations. The report was filed with Japanese naval intelligence, analyzed, and incorporated into strategic assessments of American capabilities. It contributed to Japanese confidence that American carrier forces would need to approach within 400 nautical miles of Japan to launch effective attacks. This confidence shaped Japanese defensive planning for the next 3 years. The Americans, meanwhile, understood exactly what they had achieved. On June 27, Doolittle was promoted to Brigadier General and awarded the Medal of Honor. Potter and the other navigators received Distinguished Flying Cross.
The mission was celebrated as a triumph of American ingenuity and courage. But the real triumph was quieter and more profound. Potter had solved a problem that conventional military thinking said was unsolvable: navigating across 650 miles of ocean at wave-top altitude with unprecedented accuracy. He'd done it not by developing more sophisticated equipment, but by recognizing when sophistication became a liability. The crashed B-25 scattered across China contained the evidence of this revolutionary thinking. Japanese engineers photographed it, measured it, documented it meticulously. They never understood it. They saw missing equipment where they should have seen deliberate innovation. They saw inferior technology where they should have seen tactical genius. They saw weakness where they should have seen strength. The irony persisted through the war's end. When Japan surrendered on August 15, 1945, American B-29s had been bombing Japanese cities for months using the most sophisticated navigation equipment ever developed. Radar systems that could find targets through clouds, automatic bombsights that calculated trajectories with mechanical precision, radio navigation that provided constant position updates. The technology Potter had stripped away in 1942 had been perfected and deployed with devastating effectiveness. Yet for certain missions, low-altitude attacks, special operations, long-range fighter sweeps, American forces still used Potter's dead reckoning techniques. The simple mathematics, the constant readings, the human calculation that seemed primitive but proved reliable. Even at war's end, American tactical doctrine acknowledged that sometimes the most advanced solution is to return to fundamentals. The lesson extends beyond navigation, beyond aviation, beyond World War II. Potter understood something that military establishments often forget. Equipment exists to serve mission requirements, not the other way around. When sophisticated systems fail to meet operational needs, the solution isn't always better systems. Sometimes it's recognizing that simpler tools, properly applied, can achieve results that complex automation cannot. The Japanese examined the evidence and saw American weakness. They were looking at American strength.
That failure of understanding, repeated across countless tactical and strategic decisions, helps explain why Japan lost the Pacific War. Not because Japanese equipment was inferior, often it was superior. Not because Japanese tactics were flawed, often they were brilliant. But because Japanese military culture couldn't comprehend that sometimes the most revolutionary innovation is to make things simpler. 16 B-25s found Tokyo on April 18, 1942, by trusting mathematics over machinery. The Japanese spent months analyzing the wreckage, documenting the inferior equipment, never understanding that what looked like sabotage was actually genius. Lieutenant Henry Potter removed 47 pounds of classified automatic stabilization equipment and replaced it with a $20 optical sight and human calculation. That unauthorized modification made the impossible raid possible. And the enemy never figured it out.